All right, so this problem on the last assignment was a little bit challenging, so I thought I'd do a solution for you. I also want to give you some geometrical insight. So it says, so let P be the orthogonal projection of V in Rn onto a line L. Show that P is the point on the line closest to V. All right, so it's good to draw a picture. Let's just draw a picture in 3 dimensions. Okay, so this is my Z, Y, X. Okay, and I'll take a point out here, or I'll take up point V. So there's a point in space, V, and then there's some line. Okay, and the orthogonal projection would be projecting down here, be perpendicular to this line. So here's the point P here. All right, now I want to show that P is the orthogonal, P is the closest point to V on the line. So okay, all right. Now, recall one fact that's important. The important fact here is that since P is the projection, that means that V minus P is orthogonal to the line. Or to all vectors in the line. Which is the same thing as saying it's orthogonal to the line. And you can see from the picture, right? This picture in 3 dimensions is very general, that I here at this, if I drop this perpendicular, I go anywhere on the line. If I take any vector along the line, so I shouldn't, instead of saying vector in the line, I should say vectors along the line. Okay, if I take any vector along the line, that's going to be perpendicular to the vector V. Okay, all right, now in order to prove this, I'm going to have to give an algebraic specification of the line. Okay, I can't just wave my hands. I have to do some kind of calculation. So what's an algebraic specification of the line? Right. Now, the way you determine a line algebraically is you choose a point on the line, and then you take an arbitrary multiple of the vector along the line. Okay. So let's say that so let W give the direction of the line. Okay. Okay. Then the set C times W plus, let me just choose some other vector here, U. Sorry. Is a parametric representation as long as U is on the line. Okay, all right, so I could take any point U on the line, but I could say U here, right? And then if I move from that point U along the vector W, right, then I'll be on a point, I'll be remaining on the line. I can move along W any distance. I can move C times W in up or down. C can be positive or negative, whatever, okay? So I can do that for any point U on the line, okay? So in particular, I could choose that particular point to be equal to P. All right, so that's really a key point in this proof, that the one way to specify this line algebraically is as P plus C times W, where W is a vector. Okay, okay. So if I choose U equal P, then I get the line. Then I get all points on the line can be expressed as C times W plus P. Okay? All right. Now I want to find the closest point to V. So I want to find the point having the form, right? Every point on the line has this form. So I want to find the point of having this form that minimizes the distance to V. Okay? So I want to minimize the distance from C plus W, C times W plus P minus V. That's what I want to minimize. Okay? All right, now I'm going to pull a little fast one on you. It's hard to calculate distance because you have to take a square root. I'm going to minimize the square distance. That's the same thing. Okay? So I want to minimize this quantity. All right. Now we're going to use a fact about the general fact about the norm or length of a vector. If I take any vector A, the norm of a vector or length of a vector is equal to the dot product of A with itself. So we learned that way back when we introduced dot product. Okay, so that means that this norm, C times W plus P minus V squared, is equal to the dot product with itself. Okay, and I did this on purpose. I want to group this together. Okay. All right. Now the dot product distributes. Okay. If I distribute, I can distribute the first component and the second component. So I'm going to actually get, so it's like the FOIL when you do multiply polynomials. So I get first times first, so that's going to be CW dot CW plus, and you can see I have 2 times CW dot P minus V because the dot product is commutative, plus P minus V dot P minus V. Okay? Now I'm going to go backwards because here I've got the dot product of a vector with itself. And if you know how, since dot product is a linear, you can actually write this as C squared times the length of W squared. All right? I can pull out the 2 C's and then I have W dot W, which is W squared. Here I have 2 times C times W. I'm going to write this as a minus here. Minus 2, and then this is V minus P. And this is dot product. Okay. And then here I have plus, this I can write as V minus P. The length of V minus P squared. Okay. All right, now what about this here? This is actually equal to 0. Okay? Because P is the projection, right? The point is that V minus P, if you look at this vector here, V minus B is what I said here, right? That's exactly what I said here. Let's circle that just to make, well, here I'll highlight it, okay? V minus P is orthogonal to all vectors in the line, okay? All right, so in particular, we have this here, that this here is orthogonal to all vectors in the line. So in particular, it's orthogonal to W, okay? So what we have here is it's equal to C times W squared plus V minus P squared, okay? Now, C squared, sorry. So this is minimized. Of course, this is minimized. The second term doesn't change. The first term is going to be smallest when C equals 0. Okay? So when C equals 0, so that means that P is the closest point. P is the closest point. Right? Because it's when C equals 0, I actually end up with P. Okay, so let me do a similar problem from this next section, which is kind of a generalization of the one that we just did. All right, so this one says, let K1 through Kk be a set of mutually orthogonal vectors in Rn. Prove that for any v in the space, the vector v minus the projection of v onto each of those individual basis vectors is orthogonal to each of the vectors. Okay, so let's start there, and we'll go on. But you can see that that's a little bit similar to what we did. In the case that we did with a line, we only had one vector, but here we have multiple vectors, and these vectors go from the origin. Okay, so let's take some set of vectors. Okay, I'll take two vectors here. So I'll call this K1, and I'll call this K2. We'll let K2 go this way. Okay, and let's say V is out here. And suppose V projects onto the plane here. Okay, so project onto, I'm sorry, so V would project onto each of those different ones. So I need to be careful here because K1 and K2 need to be orthogonal. So let me do this one again. I should try to do K2 so it's orthogonal. Okay, so let's just suppose that these are orthogonal. Okay, and I'll take some vector out here, V, and V is going to project perpendicularly. Well, it might project down here, and it would project over here on this one. Okay, now a very bad picture. That's what's going on. But you can see that what you're actually doing is that these two vectors, K1 and K2, determine a plane, and you're projecting onto the two components in the plane. Okay. All right, now suppose I take this vector V minus the projection, and I want to show it's orthogonal to each vector K1 through Kn. Okay, so suppose I take V minus, and then I'll say proj K1 V. I'm going to be sloppy. Well, I'll not write the arrows. Well, I'll try it. Okay, minus proj. Whoops. Okay, minus proj VK, VK. That's a kappa, not a K actually. So, but V. Okay, okay. And I want to take the dot product of this with kappa J. Okay. Okay. So what is that? That's equal to V dot kappa J. Okay, so then the first term here will be the proj of kappa 1 of V minus dot, dot, dot. And I'm going to single out this term that has the kappa J here. So there's going to be one term with a kappa J, proj kappa J V dot kappa, oh, sorry, this is dot kappa J. Okay, dot kappa J. Then minus dot, 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 proj kappa K V dot kappa J. Okay. Now the point is that these projections, this projection here, this is parallel to kappa 1. This one is parallel to kappa K. Okay. Now, the projection is parallel to kappa 1. This is kappa J, but kappa J is perpendicular to kappa 1. Okay, because they're all orthogonal. Okay, so note that kappa J is perpendicular to, or orthogonal to, kappa 1, and then kappa J minus 1, and then kappa J plus 1. All the other kappas, it's perpendicular to. Okay, and recall also that the projection of any kappa 1, like kappa 1 of V, is parallel to kappa 1, right? All right. So this vector here is parallel to kappa 1. So that means that the projection on K1, kappa 1 of V, dotted with kappa J, well, that's equal to some constant times kappa 1, because the projection is parallel to kappa 1 dot kappa J, but that's equal to 0. And that's going to be true for all the terms here except for the jth term. So all the dot products are 0 except the first one, V dot kappa J, and the projection on kappa J of V dot V dot kappa J. Okay. And there's a negative here. Okay. Okay. And you can use the formula for this, the projection formula, to show that in fact this term is this dot product is equal to this dot product. Okay. Okay. So use the projection formula. To show that V dot kappa J minus the projection, well, actually is equal to the projection of kappa J to V dot kappa J. You can work that out. Just put in the formula and you'll see. Okay, so that means that the total sum is 0, right? Because those two terms cancel out for any kappa J. Okay, for any kappa J. All right. Again, it's because if I write this out and do the inner product with kappa J, no matter what J is 1, 2, 3, all the way up to K, I'm going to get all these projections. Most of the projections are 0. Only one of these projections, only one of these dot products is not 0, but that will cancel the dot product with the first one. Okay, so that's part A. All right, and here it says illustrate the item. So that's kind of what this is. All right, so using E1 as K1, E2 as K2, and taking V to have components 1, 2, and 3. So we can do that here. So part B, what he's talking about is if let's see if I can do this. So here I have my three-dimensional axes. Okay, and this is E1, E2, E3. And he says use the components 1, 2, 3, taking V to have components 1, 2, 3. So it has 1 along here, 2 along here, and 3 along here. Okay, so that means the point, if I do this, kind of do this point here in the plane here, and then I go up 3 from here, 1, 2, 3. Okay, so that's my V. All right, V is here. Now if I project onto E1, I'm going to get, so this is 1, this is 2, this is 3. If I project V onto E1, I'm going to project right down to this point here, right? I'm going to project it right down to this point here. If I project from V down to E1. And that red line is going to be perpendicular to the x-axis. Okay. If I project to the V2 axis, I'm going to project down from V to 2, if I can do it there. And although it kind of doesn't look that way because of the perspective, that's also going to be perpendicular there. Okay. All right, so that's what's going on here. All right. All right. Now, part C says show that the projection is the vector in the span of the set of K's that is closest to V. Okay. Now, this is actually the same problem that we did before. Here we have the vector V minus this is orthogonal to each of the K's. Okay. All right. So we can write V. So I can be this a little bit more compressed than my previous previous proof. So we can write, so let's see. So you can say for any W in the span of K1 up to K, he calls it K, kappa K, okay, I can write V is equal to, let me write this vector here. Well, I'll just say it. So V is equal to W plus P minus W, and I'll define P in a moment, plus V minus P. Okay, where P is equal to this projection thing. So it's equal to the projection onto kappa 1 of V plus projection onto kappa K of V. All right. So in fact, that's the point here. That's actually going to be the point here. All right. In fact, that's the point on, well, I mean, that's the point we're going to show as the closest point to V on the plane. So this P is like the P in the previous problem. Okay. So that's telling me that V minus W is equal to P minus W plus V minus P. Okay. All right. And that's for any point, for any W in the span. Okay. All right. So let me take the same trick I took before. I take the length of V minus W. Okay. The length of this squared is equal to the length of this sum squared. Okay. But in fact, these two vectors are perpendicular. Right? This is we just showed that this is these two, that we just showed that this from problem part A. Right? Because this here, P minus W, is a linear combination of of K1 through K. Okay? Okay, since, right? Because P is a linear combination of K1 through KK, and so is W, since P minus W is a linear combination of K1, kappa 1 through kappa K. Okay? So these two vectors are orthogonal. Then you can use the Pythagorean theorem, or you can use the proof that I used in part A, and write this out as an inner product. So that means that this is equal to the distant length of P minus 1 W squared plus V minus P squared. All right. He shows the Pythagorean theorem in the chapter, or I actually proved it in part A. Okay? Okay. Now, the smallest possible value for P minus W is 0. So P minus W is equal to 0 if P equals W, or it's positive otherwise. Okay, so that means that P equals W minimizes the distance to V over all W's in the span of kappa 1 through kappa K. Okay? All right, so basically it's the same proof as the first one. You're using this orthogonality of the projection minus the original vector with the vectors in the subspace that you're projecting to. Okay, all right, that's it. Thanks for watching.